4.8, number 403. We have the limit as x approaches 0 from the right of the tan function with the tower function composed within it. Since the tan function is continuous, this should be the same as the tangent of the limit as x approaches 0 from the right of the tower function, assuming that this limit exists. If it doesn't exist, then there's nothing to talk about in the first place. But if this exists, then the answer is just tan of this result. So the whole thing really revolves around this limit having nothing so much to do with the tan per se. So we recognize this limit though as being a 0 to the 0, 0 raised to the 0, indeterminate power, and so therefore we should try to rearrange it so that we can use L'Hopital's rule on it. So let's take it out of context, not worry about the tan so much. So limit as x approaches 0 from the right of x to the x. So the usual thing we've been doing with indeterminate powers is to take the limit of e raised to the ln of this expression, x to the x. These two are totally synonymous because the exponential logarithm will undo each other because they're inverse functions and leave you back with x to the x. So there is no difference here whatsoever. The advantage on the right, though, because the way we structured it, is that we can remove the x down to the front as a coefficient on the natural log. So we'll have the limit as x approaches 0 from the right of e to the x times ln x. And this is more useful than dealing with this indeterminate power. We can deal with an indeterminate product here in a moment. What we need to do is slip this limit inside the exponential function, which is allowed because the exponential function is continuous. So e to the limit of x times ln x as x heads towards 0 from the right. All right, so now we just need to take this piece out of context. You don't have to, you could just keep the e notation throughout, but again, I find it very cumbersome and I do it in every single problem. I always remove the limit that's in the exponent here and try to deal with it. So the limit as x approaches 0 from the right of, we should now try to structure it, well, I'll just write it first, x ln x. So what do we have here? As x approaches 0 from the right, this is a 0 times negative infinity case, all right? As x approaches 0 from the right, we're heading towards the natural log's vertical asymptote, so it's heading downwards without bound. So this is a 0 times negative infinity case, an indeterminate product. So the indeterminate power we started with has now been forged into an indeterminate product, which will now change to an indeterminate quotient in the most obvious way, which is to, again, take powers of x and move them to the bottom. So this should be the same as the limit of ln x over 1 on x as x approaches 0 from the right. So now we've got negative infinity over infinity. That's a quintessential indeterminate quotient to which L'Hopital's rule applies. So now, using L'Hopital's rule, finally, we will take the derivative of the top and bottom separately and reapply the limit. So now we have a limit as x approaches 0 from the right of 1 on x for the derivative of the natural log and negative 1 on x squared for the derivative of 1 on x. Rearranging this just a little bit, we'll get limit as x approaches 0 from the right of negative x. But that's just 0, of course. So we get 0. But that was just the limit inside this power here. So the real answer is e to that result, is e to the 0th. So the limit of x to the x as x approaches 0 from the right is e to the 0th, which is 1. So now, finally, we get that the limit of x approaching 0 from the right of tan of x to the x is tan of 1. And that's how you would leave it. You're not going to be able to evaluate tan of 1 directly.